Do it again with the deployment.
Okay, so here's the drill for today. We're going to go over the LIM lab from yesterday. And then we've got another lab. There's actually 3 labs in a row. So this is the first lab, and then today we'll do the second lab, which is on vertical motion. And then tomorrow, on Thursday, we'll do one on horizontal motion. So all of them are brought to you by this idea, that force applied plus force opposing equals your net force, okay? Start with that idea. So here's what I want to look at, and this is what I was trying to get you to see in these questions. So here's the limb, right? Okay, you're trying to land this thing on the moon. So if you look at FAP, FOP, FNET. So here's that main engine. So vertically, what's always your opposing force in the vertical direction?
Where's the gravity?
Gravity, okay? So that's always negative 8350 newtons. So no matter what you do with this applied force, this force is always going to be present because you're always in a vertical gravitational field, okay? It's always trying to make you go towards the center of the moon or the earth or whatever that you're at. So no matter what, you can't get rid of this vertically, okay? You cannot get rid of it. So if you lose the engine, okay, you shut off that applied force, your net force now becomes this. So anything, this applied force is always going to be positive value because that's always going to make you want to go up, okay? You could flip the machine over and try and accelerate downward. I don't recommend that, I suppose, okay? So here's the point. Even if you shut off the engines vertically, there is always a vertical external force. Now, if you look at horizontal motion, okay, horizontally, is there an opposing force acting horizontally? No. Okay, there's no atmosphere on the moon. You want a boring job, be the weatherman on the moon. Okay, sunny, warm, or dark and cold. That's it. Okay. So there is no opposing force. So horizontally, this is what's called this like perfect inertial frame of reference. So when you fire those engines horizontally to start some motion, that's when you have an applied force. That's when you have a net force. But when you shut off those engines, inertia is just going to keep it moving at a constant velocity because there is no external horizontal force. Okay? So that's what I want you to see is that horizontally, you're going to accelerate when you fire the engines. Vertically, if you don't fire the engines, you're still going to accelerate because of the fact that there is that external vertical force. Okay. Your answers to 5 and 6, both of those should be positive numbers. And hopefully you realize that number 6 should be a lot bigger than your answer to number 5, because in number 6 you want a positive upward acceleration. So you know your answer to number 6 has to be bigger than the weight of the ship, okay? Because it weighs negative 8350. So the only way you can have a positive acceleration is if you have a positive net force, which means that answer has to be bigger than the weight of the ship. So it's kind of like flying this helicopter, okay? So if I just want the helicopter to hover, right, then the upward force is just balancing out that weight of gravity. If I want it to accelerate upward, I've got to give it more force.
Believe it, Daddy. Jack, sit up like one of those.
Yeah, hold on.
That close though.
Almost right. Okay. So now, and so that helicopter is a cool way to show that. And this is going to play out large in the lab that you're going to do today. Because we're going to be, oddly enough, dealing with vertical acceleration. So if you look at this helicopter, if you're just going to hover, the upward force has to balance out the weight. If you want it to accelerate upward, you have to still overcome the weight of the helicopter, plus it's that additional force to make it accelerate. So that's why that answer to number 6 has to be bigger than 8,350. Because if you're just exerting 8,350 newtons of force, the ship is just going to hover. So if you want it to accelerate with a positive value, you have to apply more force than that. Okay. Make sure on that graph I see when you think the net force is positive, when I think the net force is negative, when it's speeding up, when it's slowing down. Any questions on the lab? Kelsey?
On number 3, I just said something really basic. Is it supposed to be
I don't know, as opposed to acidic?
I just said
Or neutral?
acceleration has to change. Or
Huh?
I just said the acceleration has to change. Or
That's, no.
Can we talk about? I said the engine thrust has to change too.
That I can live with.
Okay.
Because look, go back to the beginning. What does the slope of a velocity time graph give you?
Acceleration.
Acceleration, right? Now, net force equals mass times acceleration. So if you look on any velocity time graph, okay, so here's any random velocity time graph. So let's say you have something like this, okay? All right, it doesn't even have to change sign. So this had a certain acceleration, right? Force equals mass times acceleration, right? Okay, so this has a certain acceleration. So now that slope changed, right? My acceleration became a bigger value. So what did I have to do to change that acceleration? What did you have to change?
The engine thrust.
Yeah, because your applied force changes your net force, and your net force determines your acceleration.
Got it.
Okay? Anything else? Going once? Food.
Okay, so would the net force be positive or positive or negative based on the slope?
Yeah,
Okay.
because your net force is the only one that equals mass times acceleration. And mass is always positive. So if you have like in this situation, you have a positive sloping line. So the only way you can have a positive sloping line is when you have a positive acceleration. The only way you can have a positive acceleration is if you have a positive net force. Okay? Go with that. All right. Anything else?
Is this slowing
Going
down?
once, going twice? So,
What? Is this?
It's slowing down here and then speeding up here.
Yeah. Is it when the signs are the
Over
same?
there, Ellie.
Ellie, why
That
did you
will
not
speed
raise
up
your hand?
and slow down
I don't
when
have a
they're
question.
different. So in velocity's positive and acceleration is
You,
negative.
I look over and it's
So
like,
decrease and then down here. I
What?
was quite good about that. And
I'm
then,
shuttling in today, is it okay if I leave Boston?
you'll be working on a lab, so.
Okay. Yo, it was cold yesterday. I saw whole guy's face not on
Yeah, you
there.
just need to put
the poor guy's face not on his face.
Yeah. Well, it was a girl, but
Did you
still.
cry?
No.
I would have.
No, there was like a necklace and they had like separated the whole skin from like.
Okay.
That sounds so cool.
You don't like that at your work
biology.
camp?
Okay,
It's like, you know.
so this lab that you're gonna do is gonna consist of two different parts, okay? One is like a simulated elevator problem. So you're gonna take a Newton scale, oddly enough, which measures newtons, and you're gonna be lifting up a 500 Newton mass. And so make sure that you re-zero it in the direction that you're gonna be lifting it. Now I'm gonna put on like a piece of string so it's easier for you guys to see. You guys don't have to use string, you can actually just hook it directly up. So oddly enough, I hold this up, and so what should the reading on the scale be if I'm lifting up a 500 gram mass? 4.9, right? Because 0.5 times 9.8 gets you 4.9. Now, so I'm just holding this, right? Mr. Taylor, is it accelerating? So what does my net force equal at this point? Goose eggs. So here's my question. Is the scale up there reading my applied force, my opposing force, or my net force?
That's opposing.
Okay. So it's either the applied force, the opposing force, or the net force.
Opposing.
Could it be the net force?
No.
Why couldn't it be the net force?
It's zero.
A net force is 0. Why?
Because it's not accelerated.
Not accelerated. So that leaves me either it's measuring the applied force or the opposing force.
Would it be measuring the applied because it's holding it up?
Yes, this is measuring my applied force. Okay?
Good job, Felix.
My opposing force, which is paying off the gravity mafia, would be negative 4.9 newtons. So if you look at, oddly enough, in terms of this equation right here, and every problem on today's lab, you start with this equation. So my net force is going to be 0 newtons. I know that because it's not accelerating. So these two forces here have to add up to 0. So the only way that can happen is if these two values are equal and opposite. So in this lab, we're going to divide everything going down as negative and anything going up as positive. So that'd be negative 4.9 newtons, positive 4.9 newtons, voila, I add up to equal to 0. So this is going to be important. Your scale is always reading the applied force, okay? Now, so what you do is you're going to hold it up, and then you're going to move it up at a constant velocity, and you're going to move it down at a constant velocity, so imagine this is like an elevator. And then you're going to accelerate it upward, and then you're going to accelerate it downward. So you can have constant velocity up, constant velocity down, accelerated upward, accelerated downward. So when you have that accelerated motion, what is your net force not going to equal? 0. Okay, now think this through in terms of like the helicopter. When you accelerate that upward, is your applied force going to be bigger or smaller than your opposing force? Bigger. Okay? If you're accelerating downward, your applied force is going to be smaller. So one of the challenges is actually getting that reading during the accelerated motion. So if you want to get fancy, you can like take your phones and like record the video of it as you're moving it, and then you'll know exactly like when you get like that maximum reading. You don't have to go through that. If you just want to like watch it and do that, that's fine. So you're going to have accelerated upward, accelerated downward, constant velocity up, constant velocity down. Now, so after that, then you've got a series of questions to answer. And when in doubt, think through this chart, and keeping in mind that you are measuring the applied force. Okay? So that's the first part of the lab. So let me go ahead and hand this out so you kind of see where we're going to go from there. That makes sense if you get the lab.
So that this had positive velocity.
I know.
Positive acceleration.
I just.
Oh, because you're going. So this was right?
That one was on the
You have. Acceleration doesn't mean the speeding up and slowing down. That's acceleration.
I like that title. It kind of has a rhyming aspect
Speeding up
to
and
it, you
slowing
know.
down matters.
Little alliteration.
With the velocity and
So I did this right,
Okay,
Yeah,
but
so
it's still negative.
what you're going to do
on this
here,
whole thing, because
okay,
acceleration is negative.
10 Newton scale,
That
up
doesn't
at a
mean
constant
speed
velocity,
is slowing
down at a constant velocity, accelerated upward, accelerated downward, okay? So, there's that. That's all you're going to need to answer all of the questions on page 1 and 2. So, and this also harkens back to the LEM lab that you just did, okay? Kind of a comparison on that. Now, when you get to question number 12, let me kind of paint the picture of what's happening on number 12. So here's this elevator, and you're going to hold 20 people. So if you're an engineer, you always plan for like a worst case scenario. It's like, okay, here's this elevator. What's a worst case scenario? 20 drunk frat guys trying to crowd into the elevator. Okay, so it's the maximum number of drunk frat guys we can put in. Okay, 20 people, you figure each one has a mass of 75 kilograms. Now, all strings, all cables, whatever, have a breaking point. So like if I take even like this string, which is pretty lightweight, and just pull on it, that's going to snap. So anything has a breaking point. So if you exceed that limit, bad things are going to happen and the cable is going to break. So what you're trying to figure out on number 12 is that what's the maximum upward acceleration that this system could have and not snap the cable. So the other way that you can kind of view that is that this is just your basic brochure sack, okay? And I've got two 1 kilogram masses in here. So if I lift it up slowly, all right, no worries, right? So I'm applying an upward force, we get a little bit of acceleration, right? Okay. And the sack doesn't break. However, if I lift it up really quickly, then I rip out the bottom of the sack. So what's the difference? In one situation, I lift it up slowly, and it doesn't break. The other situation, I lift it up quickly, and I tear out the bottom.
Inertia.
No, the inertia is going to be the same. Why is the inertia going to be the same in both situations?
Based on mass.
So only based upon mass, right? I did not change the inertia of the system. But, Zach, what did you say?
The applied force is a lot higher.
Yeah, so when I lift that up really quickly, I'm applying a much greater force to it, right? The kilograms want to remain at rest no matter what. That's not going to change, okay? They're going to have the same inertia, whether I lift that up slowly or not. And that's actually a concern if you design plastic bags, which I hate, by the way. Environmental disaster, that's a whole other story. But they can only hold so much, okay? And it's like, okay, what's your average weight of, that someone's going to be carrying when they pick it up? What's the average acceleration that people are going to have when they pick up a sack of groceries? Most people aren't going to go lift it up really quickly. Unless you're a physics teacher and you're trying to show what happens when your applied force exceeds the limit of the bottom of the string. Okay, so anyway, on number 12, you're going to try and find the maximum acceleration that elevator can have without snapping the cable. Keep in mind, you have to lift the elevator and you have to lift the people that are inside it. Okay, that's going to be the first part of the lab. The second part of the lab is going to deal with what's called an Atwood machine. So, can you turn that over here towards the object statement? Okay, so you all used this before, right? Okay. Now, when I let go of it, does the system accelerate?
Yes.
Yes. Okay. It accelerates. So what does that mean? My net force does not equal 0. So here I've got a 500 gram mass on this side. I've got the stapler on this side. Which one weighs more? 500 gram mass. So that's going to be like pulling down with a force of 4.9 newtons, right? Okay. So when I let go of it, though, gravity is pulling down with a force of 4.9 newtons. So here's my question. Since gravity is pulling down with a force of 4.9 newtons, why doesn't it accelerate at 9.8 meters per second squared?
The stapler is the applied force.
What'd you say?
The stapler is acting as an applied force.
As not the applied force, as an opposing force. Okay? So here's what we're going to do. If you look at this in terms of net force, applied force, and opposing force. So in the lab, we're going to let the bigger weight, we're going to make that the applied force. We're going to make this be the opposing force. Okay? Now, here's what I want you to think through. If I'm just holding this, gravity is pulling down with a force of 4.9 newtons. The tension in the string, okay, which is going to be this upwards, so tension is just a measure of force. So when you think tension, you think force. So if I'm just holding the system right now, gravity is pulling down with a force of negative 4.9 newtons. The string is pushing up, or pulling up with a force of 4.9 newtons. The system's in equilibrium. Now, if I just cut the string, if I just come in here and go, quick, cut the string, what's going to be the acceleration of that 500 gram mass?
Negative 9.8.
Negative 9.8 meters per second squared. So because there's no upward force opposing that downward pull of gravity. But if I cut the string, I get an acceleration of 9.8 meters per second squared. But if I've got the stapler attached, clearly that's not anywhere close to 9.8 meters per second squared. Because we're going to make this the applied force, okay? I want to make this the opposing force. Now, at the end of the day, we've got to use F equals ma, okay? Force net equals mass times acceleration. So here's the question. Which mass do I use? Do I use the 500 gram mass? Do I use the stapler's mass? Or do I use the combined mass of both of them? 80.
Both of them?
What'd you say?
Both of them?
Beautiful. Why?
Just to both contain each other.
Yeah. Here's the deal. What's the only thing that affects inertia? Mass. So when I let go of this, you have two things that want to remain at rest. You have the 500 gram mass, which wants to remain at rest, and you have the stapler, which wants to remain at rest. So that net force, the difference between these two, imagine that single force, imagine you could have just one single force acting on both of these together. So this is why, at the end of the day, when you have a system like this, you always divide by the total mass of the system. In terms of the lab today and the lab that you're going to do on Thursday, okay? You always, always, always divide by the total mass of the system. Okay, so here's what you need to do. Now, go, you got to swing this over to this side. Okay, so over on page 3, you can have a ring stand like this, a hook, and a single pulley. And we're going to have, in this situation, I've got a 200 gram mass on both sides. So why isn't the system accelerated?
Equilibrium.
It's in equilibrium, there's no imbalanced force. There's forces acting all over the place, okay? Gravity is pulling down, so if you look at this in terms of like Newton's 3 laws of motion, here's the third law in action right here. Gravity is pulling down on the 200 gram mass, but what's the 200 gram mass doing? The Earth is pulling down on the 200 gram mass. What's the 200 gram mass doing? Pulling back up, right? Because for every action there is a reaction. This is pulling down on the string is pulling up like this. This is pulling down on the hook is pulling back up like this. Okay? There you go. So right now, there's no imbalanced force. I'm not saying that there aren't forces, okay? There are forces acting on the system, there's just not any imbalanced force. So what we're going to do is we're going to take a 20 gram mass, and we're going to put that on one side. So I got this 200, so I'll put this on one side. Now when I let go of it, what's going to happen? Now it's going to begin to accelerate, right? Okay? So here's the deal. So when I let go of this, we begin to see an acceleration. So what we're going to do is that we're going to calculate the acceleration two different ways. One based upon the difference in the applied forces, and then we're going to calculate acceleration based upon measured values. So when I let go of this, what are some things that I can measure about the system? Lily, what's one thing that I can measure when I let go of this thing?
How long it takes for it to go down?
Yeah, I can measure time, okay? And I don't care which time you measure. You can measure the time that that one comes up. You can measure the time that that one goes down. I don't care, because it's going to be the same. So we can measure time. What else could I measure?
Displacement?
Oh, I can measure distance, right? I can measure how far, and again, I don't care which one you do. You can either measure how far this one falls, or you can measure how far that one comes up. I don't care, okay? It makes me no difference whatsoever. But here's the deal. You have to pick what you're going to measure from. Are you going to measure from the knot? Are you from here? Are you going to measure from the top of the hook? Are you going to measure from the bottom of the weight? Are you going to put one on the floor and then measure how far that goes up? Are you going to let go of it and then let it fall until one of them hits the floor? I don't care, right? It makes me no difference. But that's one of the most important things that you have to decide. What are you going to measure? Are you going to measure how far this one goes up? Are you going to measure how far that one goes down? what are you gonna time? Now, make sure that when you let go of this, okay, so let's say you're gonna have it like this, okay? And you're gonna let go of it, make sure that you're not stopping this at the same time you're stopping the stopwatch, okay? You want this thing still moving when you stop the stopwatch, okay? Because that's one of the most important things, because if you stop it at the same time that you're stopping the stopwatch, then you're slowing it down as part of that time. Now, here's the other thing. If you're clever, and you all are, what are you going to let the initial velocity of the system be? Yeah. Don't let it move. Like, okay, don't go like this. Okay, we'll let it start moving, and then we'll start the stopwatch. Make it simple. Okay. Let the initial velocity of that system be 0. So you're going to do that 5 trials with the 200 and the 20, and then you're going to put another 20 gram mass on here. So now you're going to have this situation. Seriously. So now what do you think is going to happen to the acceleration when I put 2 20s on one side? You're going to get an even bigger acceleration, right? Because now you have a bigger discrepancy in force. So here's what we're going to do. So here's the pulley. Plus the 20. Okay? So on page 3, I don't care, you're going to figure out what your distance is going to be. Maybe 0.4, maybe 0.5. Make it some fairly good sized distance, okay? I don't care, this is up to you. I don't care what you're going to let that distance be. You're just going to have a distance. You're going to run 5 trials, okay? Take the average of the times. If you look at your data and 4 sets of the data are pretty close together and one's way out there, redo that trial, okay? Redo that trial. Don't just say, oh, we're just going to keep it. It's going to take an average. No, if you look at your data and one's completely jacked up, redo that trial. So here's what we're going to do. You're going to know if you look at VDAT, okay? If you're clever, what are you going to let the initial velocity of the system be? 0. You're going to know a distance. You're going to know how far it moves. And again, I don't care which one you measure. I don't care if you measure how far one goes up or the other one goes down. That's up to you as a lab group. Lily said we can also measure time. So we're going to know distance, we're going to know time, we're searching for the acceleration, and we know the initial velocity is 0. So what equation relates distance, acceleration, time, and initial velocity?
V equals V naught plus VT.
D, what'd you say? V naught T plus 1/2 AT squared. Oh, that's clever, right? So my initial velocity is
0.
that goes away. So we're going to know a distance, we're going to know time, we're going to solve for acceleration. So Lexi, I need to get acceleration by itself, so what am I going to do? Multiply by 2, then divide by equals my acceleration. Okay? So show me that calculation, because everybody's data is different. So this is going to be your experimental acceleration. You're going to do that. You don't have to do this calculation 5 times. Just do it once using the average time. Okay? You don't have to calculate. I just want one average time, and you're going to calculate one acceleration. And then you're going to do the same thing with the 240 and the 200. Okay? Now, that's going to be the first calculation of acceleration based upon the collected data. Now we're going to calculate a theoretical acceleration based upon these values. So what we're going to do is that we're going to let the 220, the weight of that being pulled down, we're going to make that the applied force. Okay? So you're going to take 220 grams, divide by 1,000, multiply that by 9.8 meters per second squared. So let's make sure everybody's cool. So you've got your homecoming queen. Take 220, or 0.220, times 9.8.
2.156.
What'd you get?
2.16.
2.16 newtons. Okay, so we're going to make that the applied force. This is what's trying to drag this system. Now, you got to drag the 200 gram with it.
Wait, did I do it wrong?
I don't know.
Did you say multiply or divide?
Multiply.
Okay.
Yeah, 0.220 times 9.8.
Sorry, I heard him say divide, so I got confused. I did 0.220 times 9.8.
Yeah.
We're good. We're good.
Okay, okay.
It's just wrong.
Okay, so we're going to make that the applied force. We're going to make the 200 gram the opposing force. So if we take 0.2 times 9.8, we get 1.96, I believe.
Yes.
Okay, so this is going to this is what we're going to call the applied force, 2.16. This is going to be the opposing force of 1.96 newtons. So the difference between those two is your net force, right? Okay, so you can take 2.16 minus 1.96, there's your net force. Now, how are you going to get your theoretical acceleration? What mass are you going to divide by? The 220, the 200, or the combined mass?
Combined mass.
Always, always, always divide by the combined mass, because both have inertia, both have mass, they both want to remain at rest, okay? So here's kind of the analogy. So imagine like maybe you're the younger sister to an older brother. I'm just saying, okay, hypothetically. And so older brother is going out on a date. So he finally got this date, okay? Very excited about the date, okay? It's homecoming, right? Okay, got the sash, okay? And you're ready to walk out the door, and mom goes, as popular as your mom might be, your mom goes, hey, you've got to take your little sibling with you, okay? So right away the sibling becomes the opposing force, because you're all excited to go out, and now you've got to drag Timmy, okay? So Timmy's going to act as an opposing force to your desire to move. So this is kind of what's happening here. Gravity's pulling down on the 220. Cool, right? Now gravity's also pulling down on the 200, but not as much. So gravity's going, ooh, let's party, and then you have to drag along little brother, okay? So once you drag along the younger sibling, guess what? You can't accelerate as quickly because you now have an opposing force, okay? So that's another way that you can view this in terms of like human relations. So then you're going to do the 240 and the 200. Again, make the 240 the applied force. Take 0.24 times 9.8. Take 0.2 times 9.8. There's your opposing force. Okay. So you're going to have two theoretical accelerations, and you're going to have two experimental accelerations. Okay. Make sure you show that. Now, when you get to questions 2, 3, and 4, okay, got an asterisk that it says explain your answers. So let me kind of give you this scenario on what I want. So can you turn that down? So here's what I want you to think through. So you got the 200 and the 220. So here's the basic idea what I want you to think through. Is that scenario number 1, you're dragging along you got the 220, 200, and this thing is being dragged along, right? The other scenario is that we set it up again, and we just cut the string. So here's what I want you to think through. If I just cut the string, does that have any impact on what we're calling the applied force? So in other words, does dragging along your little brother or sister, does that have any impact on that applied force? Then if scenario number 1, we drag it, scenario number 2, we just cut the string. Then I want you to look at, oh, what's going to happen to the net force? So if this is my applied force, what's going to happen to the net force if I just cut the string versus dragging along the opposing mass? Then think through the acceleration. What would happen to the acceleration if I cut the string versus dragging the other mass with it? Okay? So that's what I want. That's the visual that I want. Scenario number 1, we're dragging it. Scenario number 2, we just cut the string and let it fall. So think through that in terms of applied force, opposing force, net force. We cut it, we drag your little sister out on the date. Okay? Good? All right, I am done. So focus on getting your data first. You have 2 distinct parts. Now, when you're going through those questions, when in doubt, if you don't know what to do, set up a chart. Go, what's my applied force? What's my opposing force? What's my net force? Also, on a lot of these, I'm going to expect you to make a sketch of a free body diagram. Applied force, opposing force, net force. Is there some of these there might not be a net force? Okay, so keep that in mind. All right, I am done. You have the rest of the time.